Oh, come on in. Okay, let's jump into this first. What do I see? I see some stuff raised to the 6th power. So I'm going to take the derivative as 6 times that stuff. The 5th power. Then I have to multiply by the derivative of that inner stuff, which is sine of 2x plus e to the 4x. Now again, you can skip this step and just actually write down what the derivative is. So, and that's what I would usually recommend. So this is going to be 6 times our stuff, sine of 2x plus e to the 4x, the 5th power, times the derivative of sine of 2x. Well, I'm seeing that as sine of some stuff. So derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And that's our derivative. For this next one, I've got tangent of some stuff. I'm gonna say the word like stuff like 10,000 times. Tangent of some stuff. And so I know the derivative of tangent of some stuff is going to be secant squared of that stuff times the derivative of that stuff. Let's just do the derivative of the stuff instead of writing out like stuff prime. So it's gonna be secant squared of x cubed over 9x plus 2 times the derivative of x cubed over 9x plus 2. But to do the derivative of x cubed over 9x plus 2, we have to use the quotient rule. So that's going to be the bottom, which is 9x plus 2, times the derivative of the top, which is 3x squared, minus the top, which is x cubed, times the derivative of the bottom, which is 9. I won't use parentheses there. It's just one term, all divided by the denominator squared. And I wouldn't simplify that unless there was a good reason to. So as you might be seeing here, the chain rule, the quotient rule, also the product rule, although not in these examples, can definitely interact with each other, right? You can have to do kind of all the rules in one problem depending on what's going on. Let's look at some more examples. Let's say we had something like, y equal to x cubed plus 1 to the 7th power times tangent of e to the x. Tangent again, sure, tangent again. I already wrote it. Excuse me. All right. So I see a lot of things going on here, but first and foremost, well, maybe not first, but yeah, kind of first. I see one function times another function. I see x cubed plus 1 to the 7th times tangent of e to the x. So I'm kind of thinking of this as my f, and this is my g, and I'm going to have to use the product rule, right? My y prime, or dy dx if you prefer, either way is fine, is going to have to be f prime times g plus f times g prime. And then to find the derivative of f, I have to use the chain rule. Right, for this piece right here, I have some stuff to the 7th power. And the derivative of some stuff to the 7th is 7 times my stuff to the 6th times the derivative of my stuff times the other function, g of x. So there's my f prime. There's my g. I'm halfway there. Now I leave the first part alone. I have x cubed plus 1 to the 7th. I have to multiply that by the derivative of tangent of some stuff. Derivative tangent of x is secant squared of x. Derivative tangent of stuff is secant squared of your stuff times what? Right. Or more generally, the derivative of the stuff, which happens to be the same as the stuff because it is e to the x, and the derivative of e to the x is e to the x. So here we've got exactly f Product rule definitely in play, chain rule definitely in play here. Or we could have something like the following. Let's call this one. We have something like f of x equal to e to the cosine of x over square root of x cubed plus 1. You know what I might do before I even differentiated this one? I might rewrite it just to make it slightly easier as e to the cosine of x over x cubed plus 1 to the 1/2 power. To me, it's usually going to be easier to express roots as fractional powers, because then I can use the power. Okay, so now to find the derivative, we have to use the quotient rule. So it's going to be the bottom part, x cubed plus 1 to the 1/2 times the derivative of the top part. So the derivative of e to the stuff is e to the stuff times the derivative of that stuff. Minus, we reverse it. I'd say vice versa, honestly. I did bottom derivative of the top, now switch it. Top times the derivative of the bottom. So the top is e to the cosine of x. And the derivative of the bottom is going to be, I've got some stuff to the 1/2. 1/2 times our stuff to the negative 1/2 times the derivative of our stuff. Then all of that's divided by, we could just write x cubed plus 1, but I'm going to write x cubed plus 1 to the 1/2 squared, even though that would simplify as just x cubed plus 1, just so we can really see what's happening there. Sorry, say that one more time. Right. So just to kind of, right, here's the bottom. Here's the derivative of the top. Here is the top. Here is the derivative of the bottom. And then, of course, the bottom squared. Other questions? Okay. Yeah. So I know we mentioned it a little bit last time, but let's do some more examples where we have kind of some chain rules and chain. I know, I mean, some of those actually had some chain rules and chain rules, but let's do a few more chain rules and chain rules. Like, yeah, let's do this one. Let's do f of x equal to square root of x plus the cube root of x plus the 4th root of x. Which looks terrible. It looks especially terrible because all these radicals. So I would definitely, before I start differentiating, let's rewrite it. Let's rewrite it as f of x equal to, so instead of 4th root of x, let's say that's x to the 1/4 plus x. And then all of that is being taken the cube root of or raised to the 1/3 power plus x. And then all of that's being raised to the 1/2 power. That's how I would definitely prefer to rewrite this. Now we have to work from the outside in. So I've got a bunch of stuff. Raised to the 1/2 power. So when we start differentiating, my derivative is going to be 1/2 times all that stuff to the negative 1/2 power. And all the stuff is right there. So it's going to be x plus x to the 1/4 to the 1/3. But then I have to multiply by the derivative of the entire inside. Great. I like doing this longer way, but the only downside is it's a lot of writing. Right? Like we definitely could have actually just started taking the derivative of this instead of writing all of that prime. But this makes it a little more clear what we're doing. But it is unnecessary if you want to skip this part. I kind of want to skip it just because it's so much writing. So we've got 1/2 times our stuff, -1/2, and then the derivative of the stuff. Well, the derivative of x plus some other stuff to the 1/3 is going to be 1 plus. Sorry, oh no, yeah, I'm doing. Sorry, yeah, I got a little carried away. 1 plus the derivative of this, which is going to be 1/3 times that stuff to the -2/3. But then what do I have to multiply by? The derivative of the inside stuff, which is going to be, well, the derivative of x plus x to the 1/4 is 1 plus 1/4 x to the -3. And I know that looks like, I know I said -2/3, my 2 on my, that really looks like a 3, not a 2. Let me just be careful. That there's a -2/3. A little bit messy. They usually are when you've got chain rules and chain rules and chain rules. Let's look at another example. Say we had something like f of x equal to cotangent sine of e to the x to the 5th plus 2. All right. Fortunately, the way this one's written, it's easy to identify what the outermost function is. The outermost function is cotangent. You could also kind of work from the inside, but I saw your teacher do something kind of weird. They're like, start with x, and then you get like x to the 5th, and then plus 2, and then e to the that, and then sine of that, and then cosine, or sorry, cotangent of that. The cotangent is kind of the last thing that's happening. I don't think you do all that to really be able to see that cotangent is the outermost thing, is the way I would prefer to phrase it. But we're definitely going to take the derivative of the outermost thing first. So I've got cotangent of some stuff. The derivative of cotangent of x is negative cosecant squared of x. Oh yeah, I was going to say that something again. So the derivative of cotangent of some stuff is negative cosecant squared of the stuff. Oh, that plus 2 is in the x one. Sorry. Times the derivative of that stuff. So the stuff is sine of e to the x to the 5th plus 2. The derivative of sine of some new stuff is cosine of the new stuff times the derivative of the new stuff. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Plus, so I want to point out that this thing I've underlined here, sine of e to the x to the 5th plus 2, all of that is the derivative of sine of e to the x to the 5th plus 2. So that right there is sine of e to the x to the 5th plus 2 prime. Right? Because there is sine of some stuff is cosine of the stuff times the derivative of the stuff. And all this right here, that's the derivative of e to the x to the 5th plus 2. Because the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So chain rules and chain rules and chain rules. That's why I like to say the word stuff, because it reminds me that they need to be multiplying by the derivative of that stuff. Okay, so let's talk more about exponential functions using logarithmic differentiation, because I think that's something that's going to come up for sure. I've definitely seen it on your homework and I've seen it on your practice exams. So a reminder first. We know that for y equal to the natural log of x, the derivative of that is going to be just 1 over x. Very useful to know. Showed it a little bit last time. Definitely want to memorize this one. And at some point here, after we talk about a few more things, I'm going to go back over kind of a list of derivative rules we should be aware of. But now, for example, we can take the derivative of lots of things with logarithms. Like, sorry, let me keep the numbers going here. Sure. Like, for example, if I want to find the derivative of the natural log of x cubed plus 4, well, just like the derivative of the natural log of x is 1 over x, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which people often like to write as just one fraction. I might write this as 3x squared over x cubed plus 4. It's a very normal thing to do, although not required. Or for example, if your function is the natural log of cosine of x, then the derivative is going to be, well, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Again, normally this isn't really necessary to simplify, but it is worth simplifying here to see this is really just equal to negative sine x over cosine x, which is really just negative tangent of x. And later on, next quarter, or whenever you take 17b, and someone asks you what the antiderivative tangent of x is, you'll be like, oh, I know a function whose derivative is almost tangent. It's the natural log of cosine. So the antiderivative tangent is the natural log of cosine almost. Because you have to adjust by a sign. And you're definitely going to, I think, now I'm pretty sure you covered that one, but well, still the idea of antiderivatives is definitely important, regardless of who actually is. So let's make it a little bit more interesting. Let's say I wanted to find something really terrible, like, do I have enough room here? Yeah, I probably have enough room here. For my function, let's say my function is the natural log of x to the 4th times e to the 7x over tangent cubed x times the square root of x squared minus 9. Wow, that looks awful. Wow, I really don't want to say that my derivative is 1 over all of that stuff times the derivative of all of that stuff. Because the derivative of all of this is really, really awful. It's a quotient rule, it's 2 product rules, it's 4 chain rules, it's so much stuff. Fortunately, we don't have. We have logarithmic rules that allow us to simplify this expression before you take its derivative. So here's what I want to point out. You see something gross like this, the natural log of a bunch of stuff multiplied and divided together, you were definitely meant to simplify it first. So we can simplify this. Here are a couple simplifications that we can do. First, we can write this as the natural log of the top part, x to the 4th times e to the 7x, minus the natural log of the bottom part, tangent cubed of x times the square root of x squared minus 9. And then, when you have the natural log of a product, you can break it up as the sum of the 2 natural logs. The natural log of x to the 4th times e to the 7x is the same as the natural log of x to the 4th plus the natural log of e to the 7x. Same deal here. You're going to have the natural log of tangent cubed plus the natural log of the square root of x squared minus 9. Or as I might write it, the natural log of tangent of x cubed plus the natural log of x squared minus 9 to the 1/2. Okay, 2 more steps all in one. One thing I'm going to do is I'm going to distribute this minus sign. And the other thing I'm going to do is I'm going to bring down the powers. So this is going to actually be 4 times natural log of x. This is going to be 7x times natural log of e. And I'll point out that natural log of e is just 1. Minus 3 times natural log of tangent of x. Minus, because the minus sign distributes, 1/2 times natural log of x squared minus 9. Haven't even started to take a derivative yet. This has all been simplification. But now we are ready to take a much, much nicer derivative. So if I'm going to find the derivative, f prime of x, constant multiples, what do? They hang out. So the derivative of 4 times natural log of x is just 4 times 1 over x. The derivative of 7x is just 7, or 7 times 1 if you prefer. minus 3 times natural log of tangent. The derivative is going to be minus 3 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff. Finally, I get minus 1/2 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff. And since I've already done so much writing, I probably wouldn't simplify this anymore. You can make this a tiny bit simpler, but not really meaningfully. So that's definitely what you want to do if you see something gross like this, where it's natural log of a bunch of stuff. You want to break it apart into as many logarithms as you can, and then after you have simplified, then take the derivative of those pieces. To do that, let me give you a slightly less terrible, actually a considerably less terrible one. Why don't you all try finding this one by first breaking it up into a couple logarithms. Let's say I have y equal to the natural log of x to the 4th times secant of 3x. I'd like you to break that up into as many simple logarithms as you can, be 2, and then take the derivative after that. Yeah. Your secant of x is secant of x times tangent. And I would say more generally, the derivative of secant of some stuff is secant of the stuff times tangent of the stuff times the derivative of the stuff. So secant's kind of weird in that the quote unquote stuff that you're taking the secant of shows up twice, which is atypical. Usually it only shows up once. So it'll be 3x times 3x. And then also times, right. Those are the steps I would take to simplify this expression before differentiating as much as possible. First, break it apart as the natural log of x to the 4th plus the natural log of secant of 3x. And then since you have a power there, you can bring that power down and say you have 4 times natural log of x. But there's no more simplifying you can do here. Natural log of secant of 3x is as simple as that second piece can be. And now we're finally ready to take the derivative. dy dx is going to be 4 times the derivative of the natural log of x is 1 over x. Plus the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative secant of 3x is going to be, well, the secant of something is secant of that thing times tangent of that thing times the derivative of that thing, which is 3. And here I would take the additional step of simplifying because I can see some secant of 3x's are going to cancel out. So I would probably rewrite this as dy dx equals 4 over x plus 3 times tangent of 3x, because this secant and this secant do cancel out. Again, not necessary, but good, just good to see. So what I really wanted to get to was, what if we have things with different bases? Meaning, like, what if I want to take the derivative of, say, I don't know, 4 to the x? So I want to remind you, just so everyone's on the same page here, the derivative of x to the 4th is equal to 4 times x to the 4 minus 1. When you have x to a power, you just get to use the power rule. But when you have 4 to the x, the derivative is definitely not x times 4 to the x minus 1. Because it's not a power of x, it's x, it's x as a power, or what we would say is an exponential function. And exponential functions like 4 to the x or 3 to the x or e to the x all have derivatives kind of like e to the x. And eventually there's a pattern we can learn, but I want to show you kind of the long way first because I'm pretty sure your teacher is interested in you being able to do these other things in this other way. So here's what I would say. Take the derivative of 4 to the x. We're going to start with letting y equal 4 to the x. And this is a usual or a very common way of attacking any sort of exponential derivative, meaning if you see a variable in the exponent, this is a time you take the natural log of both. Oh, sorry. This is the time to write y equal to your thing and then take the natural log of both sides. And the reason we're going to take the natural log of both sides is because it allows us to bring down that variable and get it out of the exponent. That is the whole purpose of doing it this way. Okay, I'm going to remind you, it's not even really implicit differentiation. It is very, very explicit that y is a function of x. We even know what it is. Y is equal to 4 to the x. So when I take the derivative of both sides of this equation, that's what we're going to do next. We're going to differentiate both sides. What is we just did it like 3 times. What's the derivative of the natural log of some stuff? Right, 1 over the stuff times the derivative of the stuff. Okay, here's one that catches people off guard every time. So let me ask you 3 quick questions. What's the derivative of 6x? Cool. What's the derivative of x times 5? Does it matter that I wrote it the other way? Is 5x still the same as x times 5? What's the derivative of x times 5? Just 5. What's the derivative of, like, say, I don't know, pi squared times x? Still pi squared. Whenever you have a constant times x, the derivative is just that constant. Or another way of saying it is whenever you have a line with a slope of 6 or 5 or pi squared, the slope of a line is the slope of the line. So the derivative is just the slope. Okay. So hang in there with me. In fact, let me write one more thing. The derivative of a constant times x is just the constant. So what's the derivative of a constant times x? Right, it's just the constant, natural log of 4. Which is approximately, I don't know, like 1.4-ish. But that's not the point. The point is it's a constant. And so when you have a constant times x, the derivative is just a constant. And then we solve for y prime. We get y prime equal to y times natural log of 4. Or more generally, or sorry, more specifically, actually, y prime equal to, well, replace y with what we actually know that y is equal to. And you say, oh, y prime is going to be 4 to the x. So very, very long story short, the derivative of 4 to the x is 4 to the x times the natural log of 4. So here's something to say about if you just have a base to the x power. You can do this process every time, but it gets to be tedious, right? I imagine your teacher probably expects you to some way to be like, okay, well, if I ask them what the derivative of, say, 3 to the x is, they could do all this. But if I look at this and I just say, if I replace the 4 with 3, I'm going to get 3 to the x times natural log of 3. And it is. It even works if my base is e. The derivative of e to the x is e to the x times natural log of e. The natural log of e is 1. And it works for any positive base that isn't equal to 1. So more generally, we have that for any a greater than 0 and a not equal to 1, the derivative of a to the x is a to the x times the natural log of a. But then things get more complicated. For example, we could ask, we could ask, what's the derivative of, say, 5 to the x squared plus sine of x? Well, we can do the same sort of thing. Whenever you're trying to differentiate something that's exponential like this, where your exponent has a variable, you can start by saying, I'm going to let y equal the thing I'm trying to take the derivative of. And then I'm going to take the natural log of both sides. And then I'm going to bring the power down before I do anything else. That's why we take natural log, because we want this thing that's an exponent to not be an exponent anymore. So we're going to get the natural log of y equal to x squared plus sine of x times the natural log of 5. And now, just like last time, we can differentiate both sides. The derivative of the natural log of y is still 1 over y times y prime. Will always be. The derivative of this function, x squared plus sine of x times this constant, the constant gets to hang out. This constant multiples get to hang out. So I'm going to get 2x plus cosine of x times the natural log of 5. If you don't love this, if you're wondering why isn't there a 0 somewhere, it's because I'm using the constant multiple rule, where I'm saying the derivative of a constant times a function is just the constant times the derivative of the function. But if you prefer, you can also think about this using the product rule and say, okay, well, it's the derivative of the first piece times the second piece plus the first piece times the derivative of the second piece. And what's the derivative of the natural log of 5? I'll give you a hint, it's not 1 over 5, it's 0. Because natural log of 5 is a constant. And the derivative of a constant on its own, if we're just talking about itself by itself, is 0. And then this part goes away. You don't ever really need to use the product rule when you have a function times a constant, but you certainly can if you're more comfortable with it. Either way, though, in the end, you're going to end up with the derivative of your function multiplied by the not derivative of the constant. The rest of this is pretty rote. We multiply both sides by y. We get y prime equals y times 2x plus cosine of x times natural log of 5. And finally, we replace y with what we knew y was equal to. You get y prime equal to 5 to the x squared plus sine of x times 2x plus cosine of x times the natural log of 5. Okay. I want you all to try one on your own. Then we're going to say a thing. We're going to say a lot of things actually in a minute here. So I want you all try taking the derivative of, let's see here, sure. 6 to the x cubed. Try that one. And by doing it this way, by writing, start with y equal to 6 to the x cubed and take the natural log of both sides. Okay, let's take a look. So taking the natural log of both sides, bringing this x cubed down in front. And then we differentiate both sides, derivative of the natural log of y, 1 over y times y prime. The derivative of a function times a constant is the derivative of the function, 3x squared, and the constant multiple just hangs out. Solve for y prime. The y prime is going to equal y times 3x squared times natural log of 6. And then y prime is going to equal y, which is 6 to the x cubed times 3x squared times natural log of 6. So here's what I want you to see, because I do think it's worthwhile. We have a couple, actually, I'm gonna hold off on that for just 1 second. Well, there's so many things to say here. But here's what I really want you to see. You can do this kind of process every time when your base is a constant, or even if your base isn't a constant. But you could also kind of skip this if you feel comfortable. What I mean is the following. We have that the derivative of e to the x is e to the x. And we also just said that the derivative of some constant that's not e, like a to the x, is a to the x times natural log of a. We also have seen in the past the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And what I'm seeing in both of these previous examples here is that the derivative of some base to the stuff is that base to the stuff times the derivative of the stuff times the natural log of the base. And that is the general pattern here. So depending on your comfort level, you can say that the derivative of a to the stuff is just a to the stuff times the derivative of the stuff times the natural log of the base. Oops, sorry. And these are kind of nice rules to remember, because you can deal with any exponential function just by knowing, well, and yeah, any exponential function where the base is constant with one of these rules. Few more things about this. There's also some stuff that happens if your logarithmic base is different. So for example, what if I wanted to find the derivative of log base 4 of x? Yeah. Well, we can kind of use the same idea. Check this out. Let's let y equal log base 4 of x. And then I'm going to rewrite this as an exponential equation. My base is 4. My power is y. It's equal to x. Okay. And now we're going to use the thing that we really just did. I know that the derivative of a to the stuff is a to the stuff times the derivative of the stuff times the natural log of a. So the derivative of 4 to the stuff is going to be 4 to the stuff times the derivative of the stuff times the natural log of 4. And the derivative of x is 1. Now I'm going to solve for y prime. I'm going to get y prime equal to 1 over 4 to the y times the natural log of 4. But 4 to the y is equal to x. So really, y prime is equal to 1 over x times natural log of 4. So it looks very, very similar to the derivative of the natural log of x. Right? The derivative of ln of x is just 1 over x. The only difference here is that you have an additional division by the natural log of your different base. So here's what I would point out. The derivative of the natural log of x is 1 over x. The derivative of log with a different base, say b of x, is 1 over x natural log of b. Or as I generally think of this, if you've got an exponential function where your base is different, you end up multiplying by the natural log of that base. if you have a logarithmic function where your base is different than e, you end up dividing by the natural log of that base. Always true. Kind of neat. Kind of a pain in the butt, but it's kind of neat. Okay. So for example, if I wanted to find the derivative of log base 3 of x, well, that would just be 1 over x natural log of 3. And of course, if we have a derivative rule, there is always a chain rule version of it. And the chain rule version is literally just replace the letter x with the word stuff and end up multiplying by the derivative. That's literally like every derivative rule we have talked about. That is really what I'm doing every time when I'm doing the chain rule version. I'm just saying, instead of doing the derivative of this function of x equals this function of x, it's now going to be this function of stuff, and it's equal to the derivative of stuff times the derivative of the stuff. Every time, every single time, that's what we're doing. So here, if I want to find, say, like the derivative of log base 3 of x squared plus 1, it's going to be 1 over, instead of x, it's going to be 1 over the stuff. I also need the natural log of 3 down there. And then I have to multiply by the derivative of the stuff. Oh, sorry, you can't quite see that. Or if I said, what's the derivative of the log of x to the 5th over cosine x? Well, first I would be clever and I would simplify this using my log rule. I'd write this as the derivative of the log of x to the 5th minus the log of cosine of x. And then I would even do one more simplification and say it's the derivative of 5 times log of x minus the log of cosine of x. And since I know this isn't the natural log, I'm going to have to end up dividing by the natural log of my base. What's the base here that I didn't write? Yeah, right. Remember we were doing all the log stuff way back when, and when we did log, log is log base 10. Exactly the log base 10. You don't need to write, but you definitely need to know. So then the derivative is going to be 5 times, let's see, the derivative of log base 10 of x is 1 over x natural log of 10 minus the derivative of log base 10 of cosine of x, or log base 10 of some stuff, is 1 over the stuff. Also need a natural log of 10 down there. And then we have to multiply by the derivative of the stuff. And if you really felt like simplifying this, you write it as 5 over x natural log of 10. Minus and minus is plus. Sine over cosine is tangent over natural log of 10. So here? Sure. So I had the derivative of log base 3 of a function. I couldn't simplify it. So I just said, okay, I know the derivative of log base 3 of x is 1 over x times natural log of 3. So the derivative of log base 3 of some stuff is 1 over the stuff times natural log of 3 in the denominator. But then at the end, I have to multiply by the derivative of the stuff. It's still the chain rule. If your inside function is anything other than just plain old x, you should be saying the word stuff and thinking I'm going to have to multiply by the derivative at some point. Okay, let's look at, there's still so many things to talk about. Okay, so the last kind of variety of this, the last kind of flavor of this is when you can have really complicated things. Actually, like for example, you could say, I want to find the derivative of y equal to 6 to the 7th of the x. And in this case, even though I could probably come up with a rule for it, it just feels hard. Like, I mean, there's a point of diminishing returns where you're like, yeah, you can make rules for other things, and we're going to do another complicated thing that you could make a rule for. But at some point, it's just like use the method of logarithmic differentiation. So if you see something with a terrible exponent, the usual way to go is say, I'm going to take the natural log of this. And I should point out, 6 to the 7 to the x is not the same as, oh yeah, this is one that always gets people riled up. 6 to the 7 to the x is not the same as 6 to the 7 to the x. They're not equal to each other. 6 to the 7 to the x, if you don't write any parentheses, means 6 to the parentheses 7 to the x. Kind of annoying, but it's how we have decided things are going to. So just for example, if someone said, what's 3 to the 3 to the 3? That's equal to 3 to the 27th power. It is not equal to 3 to the 9th power. So yeah, it's kind of interesting. So anyway, the whole reason we do this is we can bring down this power here. Then we can say that the natural log of y equals 7 to the x times the natural log of 6. And at this point, I would take the derivative because I do know at this juncture how to differentiate 7 to the x. So let's see here. The derivative of both sides, you get 1 over y times y prime equal to the derivative of 7 to the x is 7 to the x times the natural log of 7. And the natural log of 6 is just a constant multiple that gets to hang out. Multiply both sides by y. So y prime is going to equal y times 7 to the x times natural log of 7 times natural log of 6. And then finally replacing y with what it's equal to, y prime is going to equal 6 to the 7x, sorry, 6 to the 7 to the x times 7 to the x times natural log of 7 times natural log of 6. It's kind of terrible. Or as you might prefer to say it, the derivative of 6 to the stuff is 6 to the stuff times the derivative of the stuff. Oops, except they got too much in there. Times the, apologies, I blew it there. That's and then you have the natural log of 6 at the very end because you have to multiply the natural log of your original base. Sorry, I kind of looked kind of gross. I'm sorry about that. Okay. One more variety of this, I promise. There's only one more variety of this, and then we'll move on eventually. Okay, so the last variety is when you really kind of absolutely have to use this method when you have, say, the derivative of something like y equal to a function of x raised to a function of x. For example, and there's definitely, I looked at your practice exams, you're definitely gonna have a question like this on your exam, for sure. Like I would bet a lot of money. I wouldn't bet my life because you never know, but I bet a lot of money that you're gonna have a question, for example, bless you, like finding the derivative of y equal to cosine of x to the x squared power. Here, although technically you could definitely find a rule for this type of thing, you really don't want to. It's too much to memorize. The better way is to know the process that we've been doing for the last 20 minutes, the process of what's called logarithmic differentiation, where you take the natural log of both sides, simplify the right-hand side, and then differentiate. So natural log of y equals the natural log of cosine of x to the x squared power. Bring down the x squared. The natural log of y equals x squared times the natural log of cosine of x. And now that we don't have any more exponents, we can differentiate both sides. So now we differentiate. See, great. 1 over y times y prime is equal to, oh, here's a different story. Every other time we've done this, the right-hand side has just been a function times a constant. That's no longer the case because I don't have natural log of 4 or natural log of 6 or natural log of this number. I have natural log of a function. So for this type of problem, it's a little extra harder. We have to use the product rule. So for the right-hand side, the derivative is going to be the derivative of x squared times leave the other function alone plus switch it up. leave x squared alone, and then multiply by the derivative of the other function. And the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff.
We don't take the natural log of 2x.
No, because what I had was I had the natural log of cosine of x times x squared, and then the x squared gets to come down in front. Right. So stuff that's in the exponent will end up being not in a natural logarithm. All right, now we're going to simplify. We're going to solve for y prime. So y prime is going to equal y times, and I would simplify this stuff a little bit. I would write this as 2x times the natural log of cosine of x minus x squared times sine over cosine is tangent. And then finally, I replace y with what is equal to, so I get y prime equal to cosine of x to the x squared power, all times this stuff here, 2x times natural log of cosine of x minus x squared times tangent of x. This is the process. There really isn't a better way of doing a problem like this. Yeah. Some people do something slightly different, but I don't think your teacher has talked about that, so I don't even want to mention it because it's not better. I think it's actually worse personally, but some people prefer to do it that way. So, but since if you don't, yeah, I'll stop talking about it. Okay, so how much time do we have? 22 minutes. All right. What else can we say about this? Let's do one more example. Oh, no, that's fine.
It's not about that. It's just like a question about the long questions.
Long
Sorry,
questions.
the word questions.
The word questions. I don't know if I've on the practice midterms or on the homeworks.
They are on the homework, but it's like 3.5 because I think she did mention on Wednesday that they will be word questions on the exam.
Okay. Do we know what flavor of word question we're talking about? Is it like, I'm guessing it might, I was just looking at them. I feel like, I don't think there's related race. I thought related race. I was like, yeah, you check and let me know because I was, yeah. Let's do one more of these just so you all can see the process one more time. So let's say there's something kind of gross, like, I don't know. Actually, so here's what I want to point out. Here's what I think makes this problem a little extra hard. Let's say I gave you the question as the following. I said, for example, find, how do I want to write this? Yeah, I'm going to write it in the jerkiest way I can. Find the derivative of, sure, let's say we have x cubed plus 1 to the tangent of x power. So what's hard about the way I've written this is you have to do something first before you can start the process. You have to say, I'm going to, you don't have to write these words, but you have to be able to say to yourself, we need to let y equal the function we were taking the derivative of. So you have to start by saying y equals x cubed plus 1 to the tangent of x. You can't really do this process without an equation where y equals the function you're trying to take the derivative of. I don't think she'll ask it like this, but she could. And then after this, we work through the process. So then we take the natural log of both sides. So I get the natural log of x cubed plus 1 raised to the tangent of x power. And the whole reason we did that was so then what can we do with what? I don't want any more powers and exponents. I mean, exponent, I don't want any more variables and exponents. So bring that down. So I get to say that the natural log of y is equal to tangent of x times the natural log of x cubed plus 1. And now we differentiate both sides. On the left, as usual, a 1 over y times y prime. On the right, a secant squared of x times natural log of x cubed plus 1 plus a tangent of x times 1 over my stuff times the derivative of my stuff. Product rule. If this is my f and this is my G. Here's my F prime, here's my G, my F. Here's my G prime that required the chain rule. Finally, so I will say this last step you can probably do in one shot if you want to. I will show the intermediate step, but if you want to go straight to the end, you may, okay, y prime equals y, which we know is all this, x cubed plus 1 to the tangent of x, times all this, which is secant squared of x times the natural log of x cubed plus 1, plus, I would write this as tangent of x times 3x squared over x cubed plus 1. If you don't like skipping that step, though, you can certainly write the intermediate step of saying y prime equals y times all that stuff. Secant squared of x, natural log of x cubed plus 1, plus tangent of x times 3x squared over x cubed plus 1. But it's totally fine to skip this and go straight to be like, oh yeah, I know what y is. It's just the function I said y was. Cool. What is it? Well, it is really rates. Really? Okay. Right. All right. So we need to talk more about implicit then. So let's do some implicit. So the whole idea with implicit differentiation, which we've already been doing for practically all of class today, is making the assumption that y is a function of x. That's always the assumption in 17A. Why? Later on, when we get to 17, either B or C, we'll talk about x and y being different, and they'll be like functions of t, and that's a totally different thing. But for now, when we see y, the always assumption is y is just some f of x. So for example, if I have, let's say we have the following, given the equation x to the y equal to y to the x, I want to find dy dx. Plus, well, this problem is kind of gross because they usually with implicit, a lot of the times with implicit, you can just differentiate from the get-go. Here I can't really. I don't know how to differentiate x to the, I don't know, y to the x. It seems problematic. I have a function to a function, a function to a function. So I'm going to still take the natural log of those sides. I wouldn't always necessarily, but here I'm going to. So let's start by doing the natural log of x to the y equals the natural log of y to the x. And then bringing down the powers. It's dy dx, dy over dx, which we pronounce usually as dy dx. We don't say the over part. Then we're going to bring down the powers. Y times natural log of x equals x times natural log of y. And now we're going to differentiate both sides. And to differentiate both sides, we're going to have to use the product rule on both sides. Because both sides you have a function of x times a function of x, and a function of x times a function of x. This is y is a function of x. So what's the derivative of y? It always feels like the silliest question I can ask, because the derivative of y is the derivative of y. That's it. Times natural log of x. There's the first half of my product rule. Plus, switch it up, y times what's the derivative of the natural log of x. And then we'll do the same thing on the right-hand side. The derivative of x is 1 times the natural log of y, plus, switch it up, x gets to stay the same, and the derivative of the natural log of y, or the natural log of some stuff, is 1 over the stuff times the derivative of the stuff. And usually that's the first step when you're doing implicit, is to take the derivative of both sides. After you've done that with implicit differentiation, the rest of it is usually just some algebra and bookkeeping. I have to solve for y prime, meaning I need to collect all the terms of y prime on the same side of the equation. So I'm going to bring them all to the left. It doesn't really matter what you pick. If you pick the opposite side, your answer will look slightly different in that the fraction will be the negative of what I have over the negative of what I have, which will still be the same fraction. So I'm going to bring all the y primes to the left. So I have y prime times natural log of x minus x over y times y prime equal to, bring everything else to the right. I have the natural log of y minus y over x. Factor out of y prime. You're left with the natural log of x minus x over y. Still equal to the same thing on the right. Finally, divide by what's multiplying y prime. The y prime equals all of the right-hand stuff divided by all of this stuff. And that's our derivative, implicitly. Most of the time, this expression is not simplifiable. Like you just kind of, it is what it is. And yeah, we should do that one too. Let's look at some more typical examples though. Yeah, we got time. Keep going. Okay, so let's say we have something like this. Find dy dx, also known as y prime. Totally fine to write one or the other. For the following. Then we have y equal to x cubed plus 6xy minus y. Okay. So whenever you have something like this, the first step is usually to differentiate both sides. There are some exceptions, which I think I have one example of an exception. So differentiate both sides. Great. Okay, I'm gonna ask it again. I know I asked it before. What's the derivative of y? Right, it's the derivative of y. You could also, if you prefer, say it's 1 times y prime, if that makes you feel more comfortable. But essentially, every time you differentiate something with y, you end up multiplying by y prime. But it's also just easy to be like, yeah, the derivative of y is the derivative of y. Okay, the derivative of x cubed is 3x squared. The derivative of 6xy is going to necessitate the product rule. I would personally view it as 6x times y. So then the derivative of 6x is 6 times the other part, plus leave the 6x alone, multiply by the derivative of the other part, which is y prime, minus the derivative of y to the 4th, or some stuff to the 4th power, is 4 times my stuff cubed times the derivative of my stuff. Or 4 times y cubed times y prime. Just like before, bring all the y prime terms to the same side. It does not matter which side you pick, as long as all the y primes are on one side and all of everything else is on the other side. Well, since all of everything else is already on the right-hand side, I might as well bring the y prime things to the left side. I'm going to get y prime minus 6x times y prime plus 4y cubed times y prime equal to 3x squared plus 6y. Factor out a y prime. So we're left with a 1 minus 6x plus 4y cubed, still equal to 3x squared plus 6y. Finally, divide by this. The y prime equals 3x squared plus 6y divided by 1 minus 6x plus 4y cubed.
Question about why we have prime in front of 4y cubed.
Well, you mean not in front of, but like over here, you mean?
Yeah.
Yeah. Well, because what I'm really doing is y to the 4th. Y to the 4th is really a function of x, or some stuff to the 4th. And so if I take the derivative of that, the derivative of some stuff to the 4th is chain rule times 4 times my stuff to the 3rd power times the derivative of my stuff. Or writing it a simpler way, it's going to be 4 times y to the 3rd times the derivative of y. The kind of more shorthand rule of thumb people use in their brains when they're doing implicit differentiation is every time you differentiate something with a y, that you always have to end up multiplying by the y prime or the dy dx. Is there a question there? Well, so here I have y prime minus 6x times y prime plus 4y cubed times y prime. And if I factor out or divide out a y prime, well, y prime times 1 gives me back the y prime. Y prime times minus 6x gives me back the 6x y prime. Y prime times 4y cubed gives me the 4y cubed y prime. Wow. Yeah. So what I would say specifically is you're going to see something like this on your exam, where you're going to have x's and y's jumbled up together. And if you see that, you automatically should think implicit differentiation. Y is a function of x. So when I differentiate something that has a y in it, I'm going to have to multiply by y. Okay. Okay, we got a little bit of time left. We should definitely get 1 or 2 more of these because I want to show you one more thing. So let's say we had the following question. Yeah. Let's say we want to find the equation of the line tangent to x cubed plus 4xy minus 3y squared plus 8y equal to 9x squared minus 7 at the point 2, 3. So what I want to tell you, first of all, is that I see x's and y's jumbled up together. I know I have to use implicit differentiation. There's no way I can solve for y. And you shouldn't try, right? If you see x's and y's all mixed up together, implicit's the way to go. So let's start off by first asking ourselves what we really need to do. If I'm trying to find the equation of the line tangent, what pieces of information do I need to find the equation of a line? I need a slope. What else do I need? I need a point. I have a point. So all I really need is a slope, because then I can say that my equation of my line is going to be y minus the y coordinate equal to the slope times x minus the x coordinate. And unless she specifically says you need to write it in the y equals mx plus b form, I would leave it like this with obviously the value of m actually plugged in until I had time at the end of the test to go back and plug it. But if you do this, you've got the equation of the line. So don't do more work than you have. It's a good thing to do with. All right, so we need to find the slope, and the way to find the slope in calculus is by finding the derivative of the thing and then plugging it. So here's where things get kind of fun. First, we're going to differentiate both sides. Okay, derivative of x cubed is 3x squared. Again, I think it's worthwhile to think of 4xy as specifically 4x times y. 4x is one piece, y is the other piece. So the derivative of 4x is 4, multiply it by y. The derivative, or leave the 4x alone, multiply it by the derivative of y, which is 1 times y prime, this one. Minus the derivative of 3 times some stuff squared, right? Because y is some stuff, is 6 times your stuff to the first, I'm not going to write, times the derivative of my stuff. The derivative of 8y is going to be 8 times y prime. And the derivative of 9x squared on the other side is 18x. And the derivative of 7 is 0. Be careful. For some reason, people seem to miss the fact that the derivative of the constant is 0 in these problems. I don't know why. Like, we're so used to it usually being 0, but then in these implicit problems, people just don't want it to use it, but it is. Okay, so now here's the thing about this. You can go one of 2 directions here. Here is the direction you should go. You can plug in your point right now. Let's see what happens when I do that. If I plug in x equal to 2 and y equal to 3, here's what I'm going to get. I'm going to get 3 times 2 squared plus 4 times 3 plus 4 times 2 times y prime minus 6 times 3 times y prime plus 8 times y prime equal to 18 times 2. If I solve this, let's see. 3 times 4 is 12 plus 12 plus 8y prime minus 18y prime plus 8y prime equals 36. 12 plus 12 is 24, so subtract 24 from both sides. So I end up with, let's see, 8 plus 8 is 16, minus 18 is -2. So I have a -2y prime equal to 12. So y prime, which is my slope, is 12 divided by -2. So y prime is -6. And that is probably the way, not probably, it's definitely the way when you get asked this type of question on your exam, which you for sure will, it's probably the way your teacher wants you. I will point out, you could do this a different way. You could say, I don't want to do it that way. I want to make my life harder for myself. I'm going to solve for y prime first. So I'm going to do the thing we did last time. I'm going to collect all the y primes on one side. So I'm going to have 4x times y prime minus 6y times y prime plus 8 times y prime equal to all the other stuff. So 18x minus 3x squared minus 4y. Factor out the y prime. I'm left with a 4x minus 6y plus 8 equal to all this stuff still. Solve for y prime, 18x minus 3x squared minus 4y over 4x minus 6y plus 8. And now plug in. That doesn't seem like the smarter way to do this, but it'll still work. You plug in 2, 3, just doing this kind of quickly. You're going to get on top 18 times 2 minus 3 times 2 squared minus 4 times 3 over 4 times 2 minus 6 times 3 plus 8. And it's exactly the same thing. That's going to end up being 12 over -2, which is -6. So save yourself some effort and do it the easier way. Now, I'm going to be a little extra clear here. This only makes sense to do if you're specifically asked to find the slope of the tangent. Right? If you're asked to find the derivative in general, like find y prime, then you have to do it this way. But if the problem says find the equation of the line tangent or the slope of the line tangent, then you're just being asked to find the derivative at a particular point. So once you have taken the derivative of both sides, straight away you can plug in your x value and your y value. And then you still have your y primes left. You're trying to actually find out what they're equal to. You're not plugging in anything y prime. We don't know y prime is equal to. But then after we've done that, then we can go back and say, okay, if you have to find the equation of the tangent line, the equation of the tangent line is going to be y minus 3 equal to -6 times x minus 2. Or solving for y equals -6x plus 12 plus 3 is plus 15.